Good afternoon. It's 2 o'clock, so we need to get started with our lecture for today. So what we are going to be doing this afternoon is a continuation of the material that we started a couple of weeks ago on variability basics. And in this lecture, we discuss the variability interactions in terms of queuing. So we introduce the queuing notation and the measures. We also explain the fundamental relations. And then we talk about the different type of queuing systems. And we focus on two specifically. One, the MM1 queue, which has the exponential assumes the arrivals are exponential and the processing times are also exponential. And we also discuss the GG1, which assumes some general processing distributions and also general probability distribution for the arrival process. And we discuss some of the equations that are used to model the WIP, cycle time, and the WIP and the cycle time in terms of performance measurements. So the last portion of this lecture is on the effects of blocking. So far we've been studying these systems, assuming that there are no space limitation in between machines, for instance. So we are basically assuming that there's so much space that we can have as much WIP as we want to, but in reality, that's not the case. So sometimes we will have some buffers that are limited, and we have to study the implications when we have those capacity limitations in terms of buffers. So that's what this piece of the lecture is referring to, the effects of blocking. So in our previous discussion, we covered the Vut equation, which is used to characterize stations with infinite space for queuing. So again, if we have a couple of machines, we are not stating that there's a limit between these two. So we are not saying, okay, you have a limited capacity in terms of how much material you can have between stations. So we are assuming that these stations will have infinite space for queuing. This discussion is useful for seeing what will happen to the WIP, to the working process, and to the cycle time without the restrictions. But as we know, in real world system, we often have this constraint for the working process. So for example, if you go to the airport, you know that there are going to be limitations in terms of space for some of the areas. So you might need to force one of the queues to be held until that space is cleared. And in manufacturing processes, it's the same thing. Like if you have a machine that is faster, processing parts faster than, let's say, the machine that follows, at some point you have to put some stop or signal the stop in order for that queue in front of the second machine to clear out so you can continue with your process. So those are typically the real world system that we are going to face in practice. So there's going to be some physical constraints in terms of space, and also there could be some logical constraints in terms of how the production floor is managed. So if you're running a just-in-time type of manufacturing process, then you might be faced with some canvas restrictions. So you are not going to be able to move material until you have a flag that indicates that the material is needed in the station following this process. So logical constraints and physical constraints can impose this constraint, the working process. So the type of models that we are now discussing are the blocking models. And they estimate the working process and the throughput for a given set of rates and buffer sizes. These are more complex than non-blocking, like the ones that we already discussed. And they often require some type of simulation analysis in order for us to get the actual performance of the system. So these are more challenging systems. You're not only dealing with the variability in the system, but also with the capacity constraints and limitations. So trying to come up with a single mathematical model in order that will cover all these practical constraints is very challenging. So that's why we end up relying on these simulation models. But we have some results that we can discuss. So as a reminder, in this class or in this course, we are looking at these systems from these two modeling perspectives, right? We are looking at the modeling using simulation, which is typically used for these type of systems because they're challenging and they need to consider uncertainty from different sources. But we are also looking at the analysis from this traditional, more mathematical perspective, which is what we are doing from the theory point of view, which is what we are doing now. So for the MM1Q, if you look at the title of this slide, we also have a \B, which is saying that we are going to study the MM1Q, but now we are also considering the capacity limitations in terms of blocking. So, the MM1Q, but where there's only enough space for B units in the system, meaning that you now have a capacity limitation of B units. And in this notation, the Kendall notation, that's going to look like the title, right? So this is going to be modeled as a MM1. This is the Kendall notation, and now we're going to add this B, which is corresponding to the blocking. The arrival rate now, or this RA, the arrival rate, now takes it on a different meaning than it does in models with unbound queues. So now it's not only the arrival rate like we have defined for the previous models. Now it represents the rate of potential arrivals, assuming that the system is not full. So as long as the system is not full, RA is gonna represent the rate of potential arrivals. Also, this equation that we've been using to define the utilization, which is the arrival rate times the TE, which is the processing time, is no longer the long run probability that the machine is busy, but instead represents what the utilization will be if no arrivals were turned away. So now remember, if you have this capacity constraint, you might not be able to accommodate all of them. So you might need to turn some of them out of the system. So now under this MM1B system, the utilization, or RA times T, is no longer the long run probability that the machine is busy, but it will represent what the utilization will be if there were no arrivals turned away. So consequently, the utilization now can equal or exceed 100% or 1. So the utilization could be 1 or could be higher than that, based on this new definition. So under those circumstances, then we can extend our equations for the case in which we have blocking. So for the case Now we have two cases to consider. We have the case in which the utilization is not equal to 1, and we have the case in which the utilization is equal to 1. So when I say not equal to 1, that represents a utilization that is less than 1 or higher than 1. And for those cases, the average working process and throughput are given by these two equations. So these two equations only apply for the case in which we have a system that is modeled as an MM1B. Okay, so this is very clear here. So the working process and the throughput are defined by these two equations. For the case in which the utilization equals 100%, this working process and throughput will simplify, right? So basically, you can substitute these numbers into the other equation. You'll see how that would change. So for WIP, we're going to have a throughput that is going to be equal to the buffer divided by 2. So B is the buffer or the buffer size. And throughput is going to be equal to B over B plus 1 times RA, which is the same as B over B plus 1 multiplied by RA. For either case, we can use the Little's law to compute the cycle time, Q time, and Q length. And those are basically expressed based on these three equations. Cycle time is going to be equal to the working process over throughput. CTQ is going to be equal to the cycle time minus TE. And the working process in Q equals the throughput times the cycle time Q. Okay, so these are the same equations. So once you figure out the values for working process and throughput, given the type of utilization that you have, different than 1 or equal to 1 for the MM1B, then you can use those results to compute the rest, the cycle time Q, and the working process Q. So here we have an example how these equations will work and what are some of the implications. So in this system at the top, we have two machines. Those are denoted by 1 and 2. In the first machine, we have an infinite raw materials. So we don't have a limitation in terms of space. So that will be here, no space limitation. But when we move to the next machine, we have a limited number of spaces for the buffer. In this case, equals 4. And in this figure is showing that 2 of those are occupied already. So you can note that there's room for B or little b equals capital B plus 2 jobs in the system. The capital B represents the spaces in the buffer. So in this case, capital B is 4. The plus 2 comes with the spaces that are in the machines, right? So if you have one part in one machine and another part in the second machine, that's the plus 2. So capital B is the buffer, which are the 4 spaces in between 1 and 2. And then we have an additional of 2 spaces for each station. Okay, so that would be 1, 2, 3, 4, 5, and 6. So B equals B plus 2. B equals 4 plus 2, which equals 6. If we look at the model station 2, we can, we go back to this equations, right? So for utilization that is different than 1, we can make some, we can recognize some of the implications. So if our buffer goes to infinity, which is what this is representing. So as our buffer gets bigger and bigger, our working process will basically get closer to this expression, u over 1 minus u. So this will always be less than the working process in the MM1 without block. For the throughput, we can do the same analysis. If we let B be as big as possible, we force that to be close to infinity, then the expression will go closer to RA, because this expression on the left will be close to 1. So this will be, as B grow bigger, that will tend to 1. So we're going to have 1 times RA. So throughput, as our buffer gets bigger, will be closer to the arrival rate, which makes sense, right? If you don't have a capacity limitation, then as we saw previously, the arrival rate was going to dictate your throughput. It's going to get closer to your arrival rate. But that always would be less than the throughput of the MM1. And then for the cycle time, we just follow the Little's law. So again, remember that u could be greater than 1. That's possible. But this is formula is valid for u different than 1. So here's an example. In here, we're comparing the case in which we have an infinite buffer. With a finite buffer. So if we look at the utilization for an MM1 without blocking, the utilization is going to be 0.9524. That's not going to change for both systems. But the working process is just u over 1 minus u, which is 20 jobs. And the throughput is going to be equal to the arrival rate, which is 1 over TE for 1. So that would be around 0.40 or 0.0476 jobs a minute. So if we do the same analysis with the buffer, let's say a buffer of 4, the throughput is going to be, now the system is modeled as an MM1B. So we use this equation. And you see that the number of jobs per minute is now lower. So we have about 18% less throughput because of the buffer situation. And the working process, as we start doing these numbers here, it's about 1.8954, which is 90% less when compared to this width. So the MM1B system has less width and less throughput than the MM1. So it's causing a difference. Okay, so these capacity limitations are reducing significantly the amount of WEP that we can have in the system, which is also causing an impact in terms of the throughput that we're going to serve in the system. In this case, it's going to be about 20% less throughput. So you remember, based on this, you always know that these two are going to be less than the non-blocking case, and that's confirmed with this example. So now that we have covered variability, the impact of variability, I want to summarize on this slide, how can we seeking out the variability? So there are some general strategies. If you go to a system, any system, manufacturing plant or a service system, finance system, how can you identify where the variability is? Well, first, you have to look for long queues. Okay, so one of the things that I ask you to do for your project is to look for a system that has a queue, right? So because you know that there's going to be some variability that is impacting the performance of your system. So for example, variability could be in the arrival process. So you might not have the same arrival rate during certain periods of the day. And then when you're running your system with the same capacity, you should expect some queues. Looking for blocking. Focus on high utilization resources. So those are the ones that typically are creating your bottlenecks. So if you want to identify where the variability is, maybe that high utilization resource is failing often, or it's having some high setup times. So focusing on those can tell you where the problem is. Consider both flow and process variability, and use the strategy in which you ask why 5 times in order to get to the root cause of your problem. Specific targets, equipment failures, setups, rework, operator pacing. Maybe you have some operators that are too slow. Anything that prevents regular arrivals and processing times, right? So again, the setups, the failures, the rework, all those are increasing the variability in your process. And one interesting concept that I want to mention as part of this lecture is called the variability pooling. And what we're trying to do here is to, by combining the impact of these different variability sources, trying to decide where to put our efforts in terms of impact. So this variability pooling is a way to deal with the congestion effects by combining multiple sources of variability. So if you're familiar with the stock market or investing on how to invest on stocks and so on, this is one of the strategies that they use. Like they want to minimize the risk, they'll combine some stocks that are opposite in terms of their value or impact. And then once those stocks that you have on one side are having a negative performance, then most likely the other stocks that you have in your portfolio are going to have a very good performance. And that way you keep your portfolio balanced. So variability pooling is used for financial planning. So allowing you to have a diversified portfolio on financial instruments to hedge against risk. So the basic idea is that the coefficient of variation of a sum of independent random variables decrease with the number of random variables. Okay, so as you increase the number of variables, independent random variables that are bringing this uncertainty into your system, variability in your system, then the coefficient of variation is going to decrease as you increase the number of sources. And because you know that there's going to be some overlap, right? So by combining all this, your impact is going to be decreasing by combining some of these factors. So for example, the time to process a batch of parts, you have T0, which is the time to process a single part, sigma 0, which is the standard deviation of time to process single part, and the coefficient of variation, or Z0, which is equal to sigma over T for a single, or for to process a single part. So when you look at the, let's say you're considering n random variables, which is what's going to create this batch. So T0 of a batch, you have multiple, let's say, multiple parts. So you are multiplying that times T0. The variance of the batch, you can also multiply that by n. So that's going to be n times sigma squared. And then the coefficient of variation for the batch is going to be this variance divided by T squared for the batch. So if you substitute the variance of the batch, that's going to be n times sigma squared. And then T0 squared is going to be this square. That's what we have here. So it equals n squared times T squared. One of these n's are going to cancel. So the equation at the end gives you this, which is the same. You know that sigma squared over T squared equals this. So that's what we have here over n. So what that's saying is, this is the final equation, is that your coefficient of variation is going to decrease as you increase the size of the number of parts in the batch. Okay, so the sum of independent random variables decreases with the number of random variables. So that coefficient of variation, or the variability pooling, is showing you that by combining all these independent variables, you can decrease that coefficient of variation. And that's the concept. And that takes us to this final slide, in which we list the topics that we cover in this lecture 2 on variability and the basics of variability. Any questions? So now we're going to transition to the next topic, which is the corrupting influence of variability. And again, remember that from what we're trying to do with these lectures is to give you some theoretical equations or theoretical basic knowledge, so you can understand the behavior of manufacturing systems. So if we just do modeling, simulation modeling, that's fine. You will learn how to build a computer-based model or representation of a system. You will learn how to interpret the results. But in terms of the essence of understanding what's going on and why you are getting those results, you need to understand the math behind the behavior of the system, which is what we are trying to do with these lectures. We are presenting you with these concepts so that when you see that your working process is getting higher in your system, you understand why. Your cycle times are getting higher. When you run your simulation model, you have an understanding of why is that the case. Understanding those concepts can help you identify where the problems are and then find solutions. Okay, so it's a balance. We need to know how to model, represent these systems in the computer, but we also need to understand why are they behaving in that way. And that's what we are trying to do with these lectures on variability, and now the corrupting influence of variability, which is an extension of what we just discussed. So now this is the agenda. We're gonna basically summarize what we have learned into these laws: the variability laws, the flow laws, and the batching laws. So in the first two lectures, we have devoted our energy to building these tools for characterizing and evaluating variability in process time, and also in flows. Okay, so we study the impact of the variability in terms of processing. We study the blocking, and we also study the impact of the arrival rates, which is connected to the flows. In this third lecture, we use the tools or these tools to describe fundamental behavior of manufacturing systems involving variability. So to measure the performance of a serial line or a serial manufacturing line, that will be a system in which you have several stations and they're connected one after the other. That's a serial line. We have some measurements or performance measurements, such as the throughput, inventory, in terms of working process, cycle time, lead time, customer service, quality. And the evaluation mostly look at comparing this performance against some type of benchmark or perfect values. And then the relative weights consistent with our business strategy. Okay, so that's the question. So remember that our standards will change over time. So maybe you start with a certain level and then you want to increase the performance. So how is this linked to business strategy? Things like inventory reduction, can that connect to having some significant cost savings? If that's the case, then that's something that you want to explore. Will cycle time reduction result in significant competitive advantage? So for example, when Amazon started to offer this 2-day shipping service, the Prime service, that gave them some significant competitive advantage, right? Because originally people will wait a week to get their stuff or their shipments. So most people will say, well, I don't want to wait that much. I'll prefer to go to the store. But after they reduce the lead time and the cycle time to 2 days, then most people or more people started using Amazon. So that gave them some significant advantage or competitive advantage. Another question, will throughput increase help generate significantly more revenue? So if you are in charge of producing an item that has very high demand, by increasing your throughput, is that giving you some competitive or advantage or some additional revenue? So we can think about our experience with COVID. There were some items that were in high demand over the pandemic. So you as a company, this strategy of increasing your throughput might result in giving you more extra revenue. Will improve customer service, generate business over the long run. And that's another important thing. So this is not necessarily connected to your process. Well, in some sense it is, because if you're meeting your timelines, then your customer service is going to be met, so it's going to be increasing. If you're not meeting those timelines, then your customers are not going to be happy. So is that something that you would like to do, and how is that going to impact your performance? So I can think about many examples in terms of customer service, having items available, like HEV, for example, providing options for pickup. All those things improve customer service, and they have an impact on how your customers react to your business. So how is that connected to these variability laws? So variability increases whenever there is a decrease in uniformity. So as you go far from uniformity, you know that you have this added uncertainty, which is connected to the variability in the system. So for instance, uniformity decreases when interval or processing times become more disparate. So if you're not able to know for sure how many people are going to arrive to your system, then there's an increased variability in that sense. So for example, if there's a event happening on campus in which, let's say, a football game, and that's a typical, let's say, it happens on Monday. You have a football game on Monday during the day. That is a deviation from uniformity on campus, right? You don't see that happening. Never see that happening. But if something like that will happen, then you know that you're deviating from the uniformity in terms of the number of vehicles that you will see on a Monday, and that would increase the variability in many ways, like parking spaces or accessing some of the areas of the university and so on. So that's just one example. However, variability need not be the result of randomness. So for example, if a firm increases the number of products produced on a line, differences in process times may increase variability. Okay, so it's not necessarily, so variability is not necessarily related to the randomness. You can also somehow input a source of variability in your system, like the example. You increase the number of products that are produced on a specific line, then the difference in the processing times may increase the variability in your system. So control is also related to variability. System is said to be in control if its current variability level is consistent with the variation expected or inherent to that system. So basically what we're trying to say here is there will be some variability in your system, but that variability can be classified as a control variability if you know that is not deviating from the usual performance. So typically in manufacturing, we have these tools that are called control charts. And what they do, or they're used to, the use of these tools or these plots are to represent whether or not your system is in control. So these are statistical plots. If you see the picture, we have the average for the sample in the middle with a green line. And then we have two limits in red. At the top, we have the open control limit, and at the bottom, we have a lower control limit. So these limits are computed based on the performance of your system. And those are used to measure whether or not the performance of your system is within or it is in control. So for example, here we have that the average temperature of, let's say, your parts is about 600, right? So if you produce a batch and you take the average temperature for that batch, you plot that value into the control chart, and then you see whether or not that value is within these bounds. As soon as you start seeing the performance in which you have multiple values that are outside the control bars, then you can state that your system is out of control, right? So you need to stop your production and check what's happening with your system. But as long as your system stay within this bounds, like right here happens once, right here happens once and once, but then it went back to control, there's no way to be alarmed. We can get alarmed if we see multiple values or multiple samples that we are taking from the system that are staying out of control in consecutive trials. That means that something is happening with your system and you had to study what's going on to identify the causes. So control is a very important concept. You'll see these charts if you end up working in industry, you will see this in this production manufacturing lines, you'll see these plots often. So what is the variability law? Increasing variability always degrades the performance of a production system. What does this imply? It implies that higher variability of any sort must harm some measure of performance. So increasing variability always degrades the performance of a production system. So if you cannot control the sources of variability, those get out of control, you know that your production or your performance of the production system will degrade as you move forward. So what that implies is that variability reduction is central to improving performance. Okay, so we want to reduce the sources of variability or control them if we want to improve our performance. The law of variability buffering states that variabilities in a production system will be buffered by some combination of these three. You can buffer using inventory. You can buffer adding capacity. So if your system is out of control, you're not able to get the throughput that you need by the end of the day, what would you do? Add capacity, maybe overtime. You will stay longer in order to meet those performance metrics. Or you might need to add another manufacturing line in order to get the final production. And then time. So time, again, in terms of overtime and so on. Some examples: process time variability pushes best case towards worst case. Higher demand variability requires more safety stock for same level of customer service. Higher cycle time variability requires longer lead time quotes to attain same level of on-time delivery. So these are 3 examples of how the law of variability is working in terms of inventory, capacity, and time. So you have to buffer. If you have variability in production system, will be buffered by a combination of these 3. Process time variability pushes best case toward worst case. So higher demand variability requires more safety stock. So that's inventory. Higher cycle time variability requires longer time, lead time. So that's time to attain the same level of on-time delivery. Another important concept is the flexibility. Although variability always requires some type of or some kind of buffer, the effects can be mitigated somewhat with flexibility. So what that means is, if you have your operators trained to do multiple tasks, let's say at one point you don't have one of them available, you can easily move people around so you can cover the needs. Same thing with the equipment. If you have equipment that is capable of doing different products, then that gives you some additional level to control your variability. So as a corollary, buffer flexibility. Flexibility reduces the amount of variability buffering. Required in a production system. An example of flexible capacity is a cross-trained workforce. By floating to operations that need the capacity, flexible workers can cover the same workload with less total capacity that will be required if workers were fixed to specific tasks. So as I mentioned already, if your workforce is cross-trained and you need extra capacity for certain stations, then you can easily accommodate those needs because your workers are able to perform those tasks. So that's important, keeping in mind, having that flexibility. And I think a lot of companies are creating that type of flexibility with their employees now. They rotate them between areas, especially, engineers and operators, they will rotate in different areas. So they will learn the business and they will learn, they will get cross-trained on different areas around the company so they can perform multiple tasks if needed. Buffering loss. System with variability must be buffered by some combination of the following. Remember those 3 words: inventory, capacity, and time. So the interpretation of this law is, if you cannot pay to reduce variability, you will pay in terms of high working process, underutilized capacity, or reduced customer service in terms of lost sales, long lead times, and late deliveries. So you will pay at some point. You can pay to reduce the variability, or you will pay by losing some type of business from your company. So here's some variability buffering examples. So for a simple product like ballpoint pens, you can't buffer with time. Nobody's gonna back order a cheap pen. You can buffer with capacity. It's too expensive and slow. So you must buffer with inventory. So you want to have a high inventory for these cheap products. So when they're needed, you can just ship them away. They're not, I mean, they're kind of low cost in terms of production. But if you have to stop your production, set up every time you need to, you get an order, then that becomes expensive. So what you want to do with this type of product is once you set up your system, you produce enough so you can cover your needs for the foreseeable future. Another type of buffering example, ambulance service. This can't buffer with inventory. You have a specific number of ambulances in the hospital. You can buffer with time, right? Because if someone needs the ambulance, you have to go provide service right away. So you must buffer with capacity. Okay, so you need to have a certain number of vehicles located across the city or the state. So when something happens, you can move them and buffer with the capacity. And then the organ transplants. This is another interesting example. You cannot buffer with working process because these only have a limited lifetime. You can buffer with capacity, right? It's going to be wrong from an ethical perspective. So you must buffer with time. You need to have person ready, something becomes available, you have to move quickly. So now that we talk about those two, let's talk now about the flow laws. So if you're familiar with thermodynamics and conservation of energy, conservation of material, this is called the same thing. The law of conservation of material in a stable system over the long run, the rate out of the system will equal the rate in less any yield loss plus any parts production within the system. So the phrase in a stable system requires that the input to the system not exceed or even be equal to its capacity. In terms of capacity, the conservation of material laws implies that the capacity of a line must be at least as large as the arrival rate to the system. Okay, so if that's not the case, then you create these long queues, right? So you need to be capable of handling at least a certain amount. So when the arrival rate comes, you're not keeping a bunch of parts waiting. Otherwise, the working process level will continue to grow and never stabilize. Okay, so the conservation of material law implies the capacity of a line must be at least as large as the arrival rate to the system. So This connects with something that we are gonna talk about later. So for example, in an airport facility, you have a lane to do the security for your and check your luggage. If that lane is not able to process a certain number of passengers in an hour, and you get an arrival rate that is higher than that, then you most likely are going to continue to have a long line of passengers waiting in the checkpoint. And that's something that we are observing in one of our projects. So we need to find out what that capacity is, and then make sure that the arrival rate is not over that capacity. Because if that's the case, then we know that the working process level will continue to grow and never stabilize. So steady state, related to the notion of a stable system, and the long run performance discussing the conservation of material law. For a system to be in steady state, the parameters of the system must never change, and the system must have been operating long enough that initial conditions no longer matter. Okay, so for example, if you are studying a process that is a 24-hour process, let's say you're studying the New York transportation system, specifically for the subway. So you know that's a system that is running 24 hours, right? So for you to say that the system is in steady state, you must study the system under the same parameters. Let's say you're running one of these lines is running 24 hours for 7 days, so that's not changing. And the system must be operating long enough that the initial condition no longer matters. So what we mean by the initial conditions is when you have the system that is empty and you need to wait for it to become full in order to reach the steady state. Another example, let's say you are studying Walmart 24 hours operating, but then you close for Thanksgiving. So the next time you open is Friday. On Friday morning, the system is going to be empty, and it's going to take some time for the system to become operating long enough. So all, let's say all cashiers and all services are fully operating, so you can observe the actual performance of the system. So the initial conditions will have an impact, right? If any system that is open, let's say a bank, you open it at 8 a.m., nobody's there, so you're going to be the first one going into the person to get service. You'll find no queues. But as you move forward during the day, queues are going to start forming, and it's very unlikely that when you go to the bank, let's say at 12 p.m., you'll find a server that is empty. You'll find a queue, right? And that's going to be the steady state condition. Once you have observed the system long enough, you know that at some point, at any point, you'll find a queue when you get into the system. And those are the operating conditions that are typical after the initial conditions, where you open, nobody's there, you get a quick service and you leave. So for a system to be in steady state, the parameters of the system must never change, and the system must have been operating long enough that the initial condition no longer matters. What really happens in steady state is that a plant runs through a series of cycles in which the system parameters are changed over time. A common type of behavior is what we call the overtime vicious cycle, which goes which goes as follows. So overtime vicious cycle, you release work at a plant capacity. Variability causes working process to increase. Jobs are late, customer complains. So you authorize one-time use of overtime. Working process fall, cycle time goes down, backlog is reduced. You breathe sigh of relief, and then you go back to step one. So every time that you run the process, you'll find the same problems until you fix these variability causes. If you don't fix that, they will be repeating this process over and over again. So that's what we call the overtime vicious cycle. So the capacity law in steady state, all plants will release work at an average rate that is strictly less than the average capacity. Okay, so you should release work at an average rate that is strictly less than the average capacity. So if you're able to handle 200 units an hour, you don't want to release work at a 250 parts per hour, because you know you are not going to be capable of running those parts on time. So you're going to end up with what we just said. Otherwise, the system will continue to grow, the working process will continue to grow and never stabilize. So you have to make sure that you release work at an average rate that is strictly less than the average capacity. In terms of utilization, if a station increases utilization, without making any other change, the average WIP and cycle time will increase in a highly nonlinear fashion. Okay, so as a note, you cannot run at full capacity, including overtime, and this failure to recognize this leads to firefighting. So what this means, let me show you with an example. So if the station increases utilization without making any other change, the average WIP and cycle time will increase in a highly nonlinear fashion. So here we have the cycle time, and we are measuring the utilization in terms of the number of parts that are being released into the system. And here's our capacity. Okay, so that's our top capacity. And what this is illustrating is the high variability versus the low variability performance. Right, so if you have a process that is low variability process, you'll be able to get closer to your full capacity, but still your cycle time will behave in a it will go up quickly in a nonlinear fashion as you get closer to your capacity. That will happen faster if you have a high variability process. So you will start seeing that change around here. So if your release rate is about 0.7 an hour, you will observe a cycle time that will go up very quickly. For the low variability, you will observe that same change around 0.9. So that gives you some extra capacity, right? If you can control the variability. So when it gets closer to 100%, cycle time increases in a nonlinear fashion. So as you get closer to this capacity, that cycle time is gonna increase pretty quickly. So what really happens with the system with insufficient capacity, if you keep adding this rate of arrivals and you're not controlling the variability and you have insufficient capacity, what's gonna happen is that you're gonna continuously see an increase in the working process. So as time increases, the working process will increase. You will never see a decrease in the working process. So what are the mechanics of the overtime visual cycle that we just discussed? Okay, I know my capacity here. This is my original capacity. So I need to make sure that I meet the required output. So I'm gonna push my capacity and increase that capacity, let's say with overtime, so I can at least increase my production rate. So that can give me the additional units that are needed. But again, the problem is still there. That variability is still there. So you are not able to, you're not fixing the problem, you're just buffering your system to accommodate the variability that you already have in place. So remember, you buffer using time, inventory, capacity. So inlines without working process control, increasing process variability at any station. Will increase the cycle time at that station. And this is something that we already discussed. Propagate more variability, and we saw this with an example, more variability to downstream stations. Thereby increasing cycle time at them as well. This observation motivates the following corollary of the variability law and the propagation property. In a line where releases are independent of completions, variability early in a routing increases cycle time more than equivalent variability later in the routing. So we show this with an example. if you put your processing or your process or your station with the highest variability at the beginning, you know that variability is going to propagate throughout the system. So the implication of this corollary is that efforts to reduce variability should be directed at the front of the line first, because that's where they are likely to have the greatest impact. So if you are going to focus on improving your system, you want to start by looking at the stations at the beginning. You want to reduce the variability there, because as you control the variability, you know that you're eliminating the possibility of that variability propagating through the entire system. So you focus on the first, second, and then you move in that direction. Obviously, you want to look at the entire system, but the effort should be at the beginning. Okay, so I think I'm gonna stop here. We'll continue our discussion next time. Any questions? So if there's no questions, then I'll see you on Monday. Remember that on Monday, you will be doing your presentations. So presentations, PowerPoint presentations on the proposed system. I'll be providing feedback on Monday. So please come to the classroom. If you're unable to present in the classroom, then send me an email and then I'll try to accommodate your presentation via Zoom. But everybody's going to be presenting on Monday. Okay. Any questions?
No, professor.
Okay. So I'll see you on Monday.
Thank you.